had a part of our discussion in a previous class in November or so back, 3-4 months back. And I think we'll continue on the lines of structural engineering field. For general information, we have discussed on different materials that is used in structural engineering. And I think all of you might have done your exams and all over. Now we will start a second part of our original lecture, that is on loading on a structure and load effects on a structure. So I think I'll share my screen to you. Let us see. Is my screen visible to you?
Yes, sir.
Yes, sir. Good. I think we have gone through some of the major materials and major actions that is to be dealt in structural engineering. Concrete, I think we have covered. Now I think we will come to different loads that can happen on a structure. As far as a structure is concerned, by building a structure itself, we generate loads on the structure, like the dead load, basically consisting of the self-weight of the structure, or rather they are the forces that is induced by gravity. Dead load is also called as a permanent load. So any self-weight of structure as well as the weight of permanent attachments on a structure, all together we call a dead load. And then comes live loads or imposed loads. Imposed loads are need not be presenting in the structure at all times, just like the occupying person's load, part of our furnitures. Sometimes they are moving loads kind of things, like occupants may move, vehicles may move. So the direction and the positions can change, but mostly they are also in the gravity direction, that is in the vertical axis. Then there are forces induced by wind or earthquakes. The moment we build a structure, we are blocking a wind flow. And by way, we are generating a wind pressure on one side of the structure or other parts of the structure. So that's a wind load. Wind load has got an advantage that your normal wind is a small velocity wind, but when you get the peak wind, like a cyclone or similar action, we get enough warning so that we can take some extra advantage. Like if a structure is weak, we will not go into the structure at the wind cyclone peak time, that you always get a warning on cyclones. But of course, there are some kind of wind loads which suddenly, based on the temperature condition and wind condition, happens, like tornadoes and all, which you cannot predict when it come and when it blow in which direction and all. Wind also, directionally, it can happen in X, Y, and Z direction. So any of the structure directions, it may happen. Then comes earthquakes. Earthquakes are loads that is generated within the structure. You all might have read about the recent Turkey earthquakes. So the earthquake is basically generated by a movement inside the plate crust of the earth, wherein the plates move related to each other vertically or horizontally through some fault will release a lot of energy stored in that. And this energy travels in different waveform through the water, soil, and rock and all interfacing mass till it reaches some structure where the structure will be vibrated with an acceleration that is containing in the earthquake waves. And the moment we get an acceleration at the base of the structure or the founding area of the structure, this acceleration multiplied by mass of the structure is generated as the earthquake force or inertia force within the building. This force is depending on one property called mass and second property called acceleration. We don't have any control on the acceleration that is reaching the structure. It depends on the distance at which the origin of the earthquake or epicenter of the earthquake happens, or where the plates move against each other, rock plates move against each other. And the direction also, we cannot predict from which direction the structure is going to experience this acceleration. However, the second part, the mass of the structure, where F is equal to ma, Newton's equation, which is the governing equation for the inertia forces, is under the control of the designer or the builder. We can make the same requirement of a structure, like we want an earthquake, we want an auditorium or a classroom or a residence for 100 m square area or 1000 m square area. We can make it with the different materials, like it can be concrete, it can be steel, it can be wood, it can be glass, like that. So a lighter the material, we get a reduced earthquake force on the building. Aluminum is also an excellent material, which can have very light properties, but still it can be successfully used in many of the structures. Forces induced by rain or snow is another part, which we may not be familiar in this part of the earth, where in our latitude is not a snow generating latitude. So if you go to far off latitudes like Himalayas or far north or far south latitudes like 60° plus and all, the snow, which is a form of rain, and fall on the structure can get accumulated on the terraces and flat areas, thus increasing the load. And heavy snowfalls are reporting causing a lot of failures in such structures. So you can see in many of these structures in such areas where a snow is possible, have a slope roof, which is of an advantage that snow can run out of the roof by its self-weight itself. But flat roofs are not advisable in the area of snow where snowfall is expected. Now there are other loads like fluid pressure. For example, if you have a water tank or a similar structure inside the building, they can exert fluid pressure. If you have a basement construction below the ground for your building, they can have external earth pressure and water pressure from the groundwater table acting on it and things like that. See, these loads, nowadays, all the IS or international codes call the loads as actions on a structure. The loads is same as action. Action is classified into permanent action, that is like your dead loads, variable actions like imposed loads, and wind and seismic. Seismic, as you know, we are all in zone 3 of Indian seismic map, and wind for Kerala condition, it is 140 km/h peak wind, which can be approximated to 39 m/s wind speed. This wind speed is again something that we should understand, that is a 3-second gust speed. Like this can be the average wind speed of a 3-second peak wind. If you take an hourly average, for example, the total wind speed during a cyclone with a peak wind speed of 140 km per hour. It may be half of this, like 70 km per hour. So the 39 will become around 20 meter per second wind speed for an hourly average. But the hourly averages cannot be used for the design of any elements. The elements are to stand for a short-term wind. So we take a 3-second gust speed. So used speed is 39 meter per second for the Kerala region. Now other lots like snow, as we discussed, it is Himalayan, European, West, far north and far south latitudes. Temperature is also an important thing. The variation in the temperature can cause a lot of loading in the structure. But of course, as far as Kerala is concerned, it's only a small variation compared to North India. But of course, temperature is a major load which can affect when the spans or length of structure is high. Even though the variation is small, the temperature difference between the construction temperature to peak up and peak down. Like in winter, how much we can go down, and in summer, how much we can go up. So if the concrete is placed at a temperature of 30 degree or 35, 32 degrees Celsius, and in the peak summer temperature, if it goes to 45 degree or 50 degree, that variation 32 to 45 degree is the strain generating in the structure. Similarly, on the other direction also, if the temperature goes down from 32 degree, the placing temperature of concrete, to a temperature down to say 15 degree or 16 degree in the winter, that difference is the maximum strain creating load in the structure. This can be far more higher as you go to North India or far north and far south latitudes. Now coming to another type of loads, it is the crane loads. If you take factories and similar structures, we need to be install certain cranes within the structure to handle the materials that is coming in the structure, or the for factories and all to handle the machineries and things like that. So the crane is again a dynamic load wherein it picks up a load very fast, creating an impact on the structure. So it's an electric crane and all. Once we switch on, the load is carried by the crane in a momentary fraction of a second, which can generate an impact on the structure. Then comes accidental actions, which are not expected at the design stage. There are accidental loads on every structure, which never, for example, an explosion on a building. This may not be anticipated for every building in the design stage. Of course, there are certain buildings like a storage building of an explosive material, we may design for that, but not other residential buildings and all. But a blast in such a building is causing an accidental action or an unexpected loading in the structure. Now, if you look at the vertical gravity loading, the vertical gravity loading act in the vertical direction. And if you take wind or earthquake kind of load, they act in the lateral direction, horizontal direction. So it is the direction of the load again depends on which type of which part of the structure is going to carry the load. So a gravity load that normally act on the slab will transfer to a neighboring beam through bending moment and shear force. And from the beam, it transfers to the column, again through bending moment and shear force. And then from the column, it travels down to the foundation through the vertical axial compression or axial tension kind of action. Now, as far as the horizontal wind load or earthquake load is concerned, that is carried by a shear wall sometimes or a frame occasionally. And this load is again transferred. All the loads has to reach the foundation finally and to be going back to Mother Earth for final carrying. And first, what we structural people should look into is the global stability of the building. If a horizontal load is acting like that, whether the structure will slide or whether the structure will overturn. So these things are to be taken care in the first go. And once this is taken care, the individual structural action and individual structural members are to be designed for the corresponding loads. So if you look at the loads or actions, if you put it 100 kilonewton on the top of a masonry wall, it is carried by a direct compression in the masonry, elements of the masonry. And then if you are hanging the same 100 kilonewton through a string or wire rope from the roof, the load is carried by direct tension. So the position of the load, type of load will tell us which type of force that is generated in the structure, compression, tension, or similar other thing. So assuming the 100 kilonewton load I'm supporting on a beam or a slab, the load is generating a bending moment and a shear force on the structure for transferring it safely back to the support and then to the soil. And of course, there can be loads which can generate torsion in the structure, like a cantilever sunshade from a beam. For example, a beam is there and a cantilever sunshade is there. So the sunshade will generate a twisting action on the structure. So a torsion can be another type of load on the structure. The loads or the actions, and again classified further into deterministic loads. Like you can say more or less precisely the magnitude of the load. They are permanent actions like dead loads, superimposed dead loads. Superimposed dead loads is nothing other than the materials that is added to the structure whose self-weight will act. I'll give you an example, a flooring, a floor tile, we add a floor tile, we add certain screed below the floor tile. So that is a superimposed dead load. It is not the self-weight of the structure, which is the dead load. The self-weight of the flooring will go into the superimposed dead load. On a rod or a bridge, if you do a wearing coat on the top, that is you might have seen the tarring of the rod on the top of bridge. So the beam and slab cause this self-weight or the dead load, whereas the tarring on the top will cause superimposed dead load. Now then the load can be further classified into variable loads or probabilistic loads. These actions consist of imposed loads or live loads, and again can be subdivided into static or dynamic. A load that is constant in direction and magnitude is called a static load. The load either changes in direction or magnitude is called a dynamic load. The load can be a moving load. The load can be wind or seismic. All these things are further not a fixed magnitude. They are all calculated by theories of probability. That is during a lifetime of a structure, which can be anticipated or estimated with the different values of lifetime for different structures. What can be the probabilistic average loading acting on the structure? Based on that, we take. Then comes accidental actions. Accidental actions are blast, impact, all those things. As we already discussed, this may not have decided or estimated at the time of design of the structure. They are all evaluated as a probabilistic value or probably with a factor of safety built into the mother structure. Now the loads or actions from the imposed loads or live loads are further divided into a leading live load and an accompanying live load. A leading live load is the load for which we design the structure. For example, if you take a factory, the crane load or the machineries that is in the factory will go in the classification of leading live load. Whereas the live load on the roof, you can say it is an accompanying live load. It may or may not happen along with the leading live load. So the difference is we put full factor of safety on the leading live load, but we put only a partial factor of safety on the accompanying live load. So the live loads, for the purpose of design, we divide them into leading and accompanying. Now coming to seismic. Seismic design, as you all know, is a major natural calamity, and out of all natural calamities classified as earthquake, wind, flood, fire, and all similar natural calamities, 47% of human fatalities happen during an earthquake. And it is estimated that 35% of the economic loss also can be attributed to earthquake, which you have seen in a day's earthquake. Turkey has lost 45,000 persons' life or more. Rather, they have not estimated it precisely. Now, the seismic load, as we discussed, an earthquake happens at some point where a rock slips, which is happening somewhere inside the earth, and then the waves travel either vertically upwards or sloping along the soil, and whatever wave that strikes the earth's surface again travels through the surface as a surface wave. And this body wave also reaches the structure. This may not reach simultaneously. This happens, the surface wave and the body wave may reach the structure at different times, and then it will start vibrating the structure at its base. And the moment you get an acceleration that is reaching the base of the structure, in turn, the mass of the structure multiplied by that acceleration will generate a lot of inertia force inside the structure, causing the F is equal to ma equation to act and giving us a lot of horizontal load. And as you see, the moment the earthquake shakes, the F is equal to ma inertia force act in the opposite direction, because the structure is inertial to move along with the base. It is just like we are all standing in a bus and the bus starts suddenly. We tend to fall in the opposite direction. Just like that, the foundation of the structure starts vibrating or moving, then the structure tend to fall in the other direction. And this inertial force has to transfer back to the soil or foundation through the walls or columns and the founding elements foundation, whether it is strip footing, isolated footing, or piles. Now, the seismic design criteria, as you see it, can be divided into minor or frequent earthquakes. These are called happening very frequent. Maybe every day you may get some vibration which you may not feel at all because of the surrounding incoming vibrations from a vehicular traffic or a normal other actions are more than that. And they are not supposed to cause any structural damage in the structure. They most of them go unaware. You may feel some of them in the night, calm condition, sleeping condition. Otherwise, they may not be felt at all. There can be moderate earthquake, which can be felt in the daytime, but should not cause a significant structural damage. They can cause some non-structural and repairable damage, like your glass, window glass is broken and things like that, but not a structural damage. And then comes a major earthquake and infrequent. This is not expected to happen once, more than once in a lifetime of a structure. And that even is a rare event. The one that happened in Turkey recently. It is not expected to happen every day. It can happen only once in the lifetime of a structure. And it may not even happen during that time, because in the design side, we take once in 500 years as the maximum peak earthquake, maximum considered earthquake, or MCE, it is otherwise called in the design. And this 500-year repeating earthquake need not fall in the 100-year lifetime of our structure. Our normal structural life we take as 100 years, any building or normal bridges. Of course, special structures are designed for a much larger life, like 150 years or 500 years like that. And this major earthquake is expected to cause severe structural damage, but it is not expected to cause a total collapse. The damages that happens may be beyond repair, and we may have to break the structure and discard the structure after such an earthquake, but it should not fall on the head of the people occupying the structure, or the people inside the building should be able to walk out of the building after such a major earthquake. The structure should be so proportioned that it can stand without collapse in a major and infrequent earthquake. But it can have some very little damage during a moderate or a minor earthquake. So that is the psychology of the earthquake design used all over the world. And we in India also use same conceptual methodology for designing the structures against earthquake loading. This is because if we try to design the structure for the full earthquake load, of course, there are structures that is built for the full load, like a nuclear power plant, wherein the consequences of failure of such a structure is much higher than the effect of earthquake itself. And a nuclear power plant is designed for almost 100% earthquake force, so that it will not have any damage even in the peak earthquake. So the concept of structural design, seismic design, is structures are designed for a much lower seismic force than what they may actually experience during the peak earthquake during their lifetime. So it is explained here that during the peak earthquake, if the forces are F, we design it only for a much lower force, normally 1/10 of the expected earthquake force. And this reduction is compensated by utilizing the ductility in the structure, redundancy in the structure, and overstrength in the structure. So all these parameters will help us in the event of a peak earthquake, and we put a very ductile structure to prevent a collapse prevention. The structure will damage, but it will not collapse on the head of the people who stay inside the structure. And the ductility is nothing other than the deflection gap available between your yield and ultimate failure. Between the yield, after the yield, before the ultimate failure, we get a long strain range on which the structure will carry the load without failure. So this is called the post-yield deflection capacity of a structure, is called the ductility of the structure. Now you can see a concrete, a very brittle material, get a highly ductile property by making it ductile by providing more number of stirrups or the lateral confining reinforcement to that in such a way that the concrete inside the confining element will remain more ductile than brittle. So you can see the damage for an earthquake affected building happens very close to the beam column junctions. Every damage is very close to lintels or the beam column junctions. This is also a junction of the lintel. The wall is totally broken. So this is also a junction of the lintel. So all such areas are getting the damage area. So such areas are to be protected by very closely spaced stirrups to prevent collapse of the structure. The structure can damage to this level, but the people inside should be able to walk out. These are all, we are talking about the earthquake that is happened in Turkey or similar order, which can happen only once in the lifetime of a structure, not every day. And it may not happen at all also during the lifetime of the structure. By the way, what is the time up to which we can continue?
Till 9 o'clock.
Till 9. Okay, thank you. So the ductility is induced in the structure by providing, as you have seen, the stirrup in this case, a folded 135-degree stirrup from the normal 90-degree direction. So this angle from this horizontal line to this folded stirrup is 135 degrees, 90 plus 45. This leg also, as you take this vertical leg, 90 plus 45. So it is 135 degrees. So this 135-degree stirrup, you can see closely in this photograph that it is bent like that in a column. This will help us to anchor the stirrup itself into the core concrete, which is protected by the stirrup. If you give a 90-degree bend, once the cover concrete is fallen, we lose the capacity of the stirrup itself to protect the concrete. So to prevent that, we fold the stirrup back into the core concrete so that the concrete which is protected will protect the stirrup also, which is actually giving a confinement to the concrete. Now, it need not be the structure alone that is damaging. The soil also can cause damage. The very saturated, loose, sandy strata, which we see in the coastal stretch of Kerala, right from Kannur to Trivandrum, in Charthala, Alappuzha and all, where the N value or the SPT test value of the soil is less than 10 and it is saturated with water. On the event of vibration, it loses its shear strength completely. And when it loses its shear strength completely, it behaves like a liquid and it can no more support any load. So till vibration, it can carry the load and the vibration will cause the shear strength to lose. If it is saturated and if it is loose, that is excess pore water pressure is there. So that action is called soil liquefaction. Soil liquefaction is a stage in which the soil shear strength happens to be zero due to a vibration. And this happens for such soils where our N value is less than 10 or very loose condition and the soil is saturated sandy soil. For clay soils, this will not happen. Now you can see the accidental action. We discussed this slightly before. Is an accidental load is a load which is not expected at the time of design. We cannot anticipate this load and design for this load. An example is shown here. This is nothing other than the twin towers that was hit by an aircraft in 2011. And then it get exploded inside the building. And finally, the building itself is collapsing. So such an accident and accidental load was never anticipated during the design of such a structure. So such loads are also possible in a structure. Now the structural systems that used to resist the loads what we discussed are spanning in different ways. There are structural systems that span horizontally, systems that span vertically. So all these things are required to carry the different actions or loads we discussed. Now, for example, horizontally spanning elements are beams and trusses. The beams is nothing other than, you all know, it can be steel, concrete, timber, aluminum or anything. Then you put a load on the top, it will have certain bending moment, it will have certain shear forces, and finally the load travels to the support through the bending moment and shear force. And then comes a truss. In case of a truss, there is no bending moment or shear force, but they are converted into the axial tension and compression on each element of the truss, and through which it transfers to the support, and from there to soil. And there can be some trusses wherein, the truss is basically a structure in which you can triangulate. Every element can be a triangulated element. Now, if we remove the diagonals and just keep only verticals, it becomes what is called a virendial truss. So this is not a triangulated truss. You cannot, here a normal truss, there is a relation between the number of nodes and number of members. So such trusses, a virendial truss, this relation will not be held. So these are special type of trusses, which is a combination of a beam and a truss. So they have some amount of bending moment, some amount of shear force, and then some amount of axial force. So all together, some tension, some compression, some shear, some bending moment, all together it carries the load. So there are cases in which we use a virendial truss or a virendial frame. It is also called a virendial frame occasionally. You can, of course, you can Google it and find out what different photographs and things like this of a virendial truss. And normal truss and beams are different horizontal spanning mechanisms. The plates is another way of spanning the load horizontally. Whereas it's a slab kind of situation. They are one-way or two-way depending on the support condition and the length and width ratio. There are one-way slabs, there are two-way slabs, and then there can be flat slabs or flat plates, where we use the pointed supports. It's a flat slab or a flat plate is nothing other than the columns only, there is no beams. And for your kind information, this is the structure that caused the maximum failure now in the Turkey earthquake. The buildings that failed or collapsed was majority conforming to this type of structure. So this is not ideal for a earthquake sensitive area, the flat slabs and flat plates. Okay, now plates is one method of, but our normal slabs which we use in a residential condition is a one-way slab or two-way slab resting on masonry or on beams. They are all capable of carrying the seismic load, but not a flat slab, wherein beams are eliminated and only columns, only plus plate, the slab is available. Now coming to one-way plates, there are band beams that is used. They are very shallow beams passing along the beams. There are flat slabs, flat slate. Everything is a horizontal spanning mechanism. We can as well use an arch for a horizontal spanning. So if you have a load there, the arch will take the load as a membrane or axial compression to the support. So arch is a horizontal spanning mechanism. You can see some typical arch photographs here. So these are all semicircular arch. This is also a semicircular arch. You can have segmental arch as well. The bottom one is a segmental arch, wherein you need vertical and horizontal supports for the arch support. This we can have a vertical support alone. You don't require any horizontal support. So for the segmental arches, which is not a semicircular, you need both vertical and horizontal supports. Now coming to trusses, when the loads are coming, they bend as a beam, but no bending moment or shear force is generated. All the members, the top chord will become a compressive member. The bottom chord will become a tensile member. The diagonals will become, these diagonals will become tensile members. If the diagonal is in the opposite direction, it will become a compressive member. And if this is tensile, then this becomes compressive, like that. It becomes a axially loaded system. So the forces in the members can be taken something like this. The verticals are in compression, diagonals are in tension, and then your top is in compression, bottom is in tension, like that. You can see a typical truss here, a photograph of a truss that is used between two columns. Then comes frames. The frames are basically elements that is rigidly connected at junctions. This junction should be capable of transferring the moment across the beam and columns. Then only it becomes a frame. The frames can be used to carry both vertical loads as well as horizontal loads. So if you have an earthquake or a wind load, if there is a frame, the frame will contribute to carry the earthquake or the wind load. You can see a frame here. This is a frame element. You can see two vertical pillars and a beam that is carrying the bridge load. So that's a frame here. This is a flat plate. As we discussed already, this is the one type of structure which created the maximum collapse in this recent Turkey earthquakes. Previously also in various earthquakes, it has proven that these are very weak in carrying horizontal loads. You have only the columns and the slabs. There is no beams connecting the columns. So there is no frame. If you require a frame, you need a column beam combination. There is no column beam combination, only columns and flat plates. It's a pure flat plate. It's called a flat plate. Now this is a folded plate, another system wherein you can, just like a folded paper, the plate also can be, the concrete or steel plate also can be folded to carry long span loads, a folded plate system. Shells are another system which can be used to transfer a lot of horizontal spanning mechanism. You can see this shell can carry loads depending on the doubly curved shells. This is a hyperbolic paraboloidal shell. So they have a tension in one direction, compression in other direction. So this is called a doubly curved because it is curved in X and Y direction. Whereas these curves are singly curved. This is curved only in one direction. The other direction it is straight. So they can be used to span across. This big cantilever is spanning because the shell is there. The curved shell is acting as a beam of full depth from this point to bottom point. So this is also a shell, singly curved shell. From this support to the opposite support, it can span 30 meter, 40 meter, like big spans. Here itself, you can see one man is standing there. Comparing to that, what is the span here? Maybe 2, 4, 6, 8 meters. Huge spans it can span. So shells are all highly capable structures. Only disadvantage with the shells is that you need a special formwork to cast them. So the formwork itself is costly, 1. 2, concrete as a material is very difficult to cast in that shape unless the formwork is provided on both sides, top and bottom. Otherwise, the concrete may not be properly compacted if you shutter it in one side alone. So these are the disadvantages with shells. Its formwork cost is very high. Now the vertical stability is achieved in a building through columns, through shear walls, through tubular frames, bundled tubes, etc. Now we will look into different systems that is used to carry the horizontal loads. They are basically carrying the horizontal loads, wind and earthquake kind of thing. You can see the World Trade Center, which we have seen a photograph just a few slides back as the accidental loading. The World Trade Center building, which is a tubular structure. That is, its outer core is made into a big tube, a square tube, and that tube is fixed at the base and standing all the way up to the roof, so that any horizontal load is taken by the outer core of the structure. So it's a tubular structure. And this is where the tube need not be always square, rectangle, or circle. It can be of very odd shapes. This is a elliptical core. Now you can see elliptical core that is split to give a waterway to go inside. So that is a structure that is provided, tubular frame provided for the Tamir Tower in Abu Dhabi. It's a very beautiful, aesthetically nice structure, but it carries its horizontal loads through the outer tube that is going into the structure. Now, coming to how we proportion or size these members, the design of the elements. When we come to design, from the loads to the structure to the design, you can see we use different methods of design. Some of them you might have studied, some of them you will be studying. So originally, what we used is a working stress method or allowable stress method. Allowable stress method is a method in which we limit the stress in each elements or each material, limited to certain allowable or working values. For example, concrete, as you know, is M20, M30. It's all called FCK value or the 28th day cube strength value. Of FCK equal to 30, we limit that to 6 Newton, that 30 to 6 Newton per mm square for the compression, or the 9 Newton per mm square for the bending. Like that, an allowable stress will be allocated to that particular material. So when we check the actual stress in the beam or column, we limit it to that particular stress. This is called the working stress method. So we give the full factor of safety into the material element maximum stress. So if it is steel, you know its yield strength is 250 Newton per mm square. However, in working stress method, we limit the value of allowable stress in the steel to 150 Newton per mm square in compression or tension, or 165 Newton per mm square in bending compression or bending tension. So this is called the working stress method. Now this is a stress-based method. Now in the case of limit state design, which has later come into all design fields. Now you might have studying the concrete, steel, pre-stressing, everything in the limit state design. Of course, the soil or the foundation designs are still in working stress method, but soon the IS codes, which is under preparation in the draft forms, are going as per the limit state design for the soil also, is splitting our factor of safety into two, and one part is applied on the loads, other part is applied on the material. So in the limit state design, we divide the strength and serviceability as into two parts and dealt separately. The serviceability is not given much importance in the working stress design. We take a presumption that by limiting the material stress, our serviceability is automatically satisfied. But in the limit state design, both strength and serviceability is to be dealt with separately. We take a higher strength allowable in the material, but at the same time, we check Serviceability like deflection, crack width, corrosion, fire resistance, all this comes into serviceability. Serviceability in a separate way. So they are dealt separately. Now this is a tension structure, tensile fabric structure. By the way, I don't know whether we continue today or we continue in the next class. It is 9 o'clock, I think.
So we can continue in the next class.
We can continue next week or?
Yes, sir. Hello.
Okay, then you take over, and I think I'll keep this point at which we stopped, and I'll take into account next Thursday.
Okay, sir. Hello, students. Anyone has any doubt? Thank you all for joining. Thank you, sir.
Okay, so we meet in the next Thursday. So by the time if they can come out with some questions, you can pass it to me, and we'll keep those also answered. Okay.
Okay, sir.
That is some area where they require some extra explanation on whatever we have covered today. I can give them some photographs, sketches, or something similar, videos or something. But we should know what they want to know, because there should be a two-way communication. Then only the class can be going successfully. We should know what they are looking at, what knowledge they are looking at, or what they are not understanding. So try to gather some questions or the queries so that we can make the classes more effective in the next day. Okay.
Okay, sir.
Thank you, sir.
Okay. Thank you. Thank you very much.
Thank you, sir.